Next we have exercise 13, and in this one we have to prove proposition 12.1.19. So let us first recall the statement of the proposition. It is about the discrete metric. Let X be any set on which we have the discrete metric. Then X will be a metric space with respect to this metric. And there is a sequence Xn where n varies from m to infinity in X. That means these individual terms of the sequence are points coming from X. And also there is another point X in X. Then the sequence converges to that point X with respect to the discrete metric if and only if there exists an integer capital N greater than or equal to the smallest value of the index n, such that all the terms of the sequence Xn are equal to X starting from that integer, starting from that value of n. So let's prove this. So we first assume that such an integer n exists for which this thing happens. So I write, if such an n exists, then the discrete metric distance between xn and x is equal to 0 for all n greater than or equal to n. Why? Because for this type of n's, xn is actually equal to x, so obviously the distance would be 0. But then if you think of the sequence whose terms are these real numbers, then that sequence is constantly 0, is having 0 terms starting from this n when n is equal to capital N. So the other values of n that come before n, for them however this distance may be something else. Well, something else in this case of course is 1, because the discrete distance has only 2 values. Discrete metric takes on only 2 values, 1 and 0. So maybe the first few terms are 1, some of them are zeros also, but starting from this value of the index n, we constantly get 0. So that sequence of real numbers obviously is converging to 0. But then what happens? Then by the definition of convergence of a sequence in a metric space, the original sequence xn converges to x with respect to the discrete metric. So we have got one half of our plane. Now we are going to prove its converse. Conversely, we assume this. So this is our hypothesis now in this second half of the solution, that the sequence xn converges to x with respect to the discrete metric. Then we know what convergence means. For an epsilon, there is an n for which those conditions are true. And that's what we are next going to write with this value of epsilon, 1 divided by 2. Actually, any positive real number less than 1 would work here. I have just simply taken 1 divided by 2. So for this value of epsilon also, because the sequence is converging, there exists an integer n greater than or equal to m, such that the discrete distance between the terms xn and x will be less than or equal to this epsilon for all n greater than or equal to n. However, we already know that the discrete distance can only take 2 values, can only be 2 values, 0 and 1. Because these distances cannot be 1, being less than or equal to 1 over 2, so all of them have to be 0. So that is why all of them are 0 for all n greater than or equal to n. But this just implies that these xn's are equal to x, because after all it's a metric. So 0 distance is obtained only when the 2 points are equal between which you are calculating distance. So that is how you get the fact that xn is constantly x for all n greater than or equal to n. So that's the solution. This type of sequences, not just in a metric space, I mean anywhere where eventually all the terms become constant, are called eventually constant sequences. So that means this proposition is stating that in a discrete metric space, only eventually constant sequences are convergent, nothing else. So let's see another one next. In this next exercise, we have to prove proposition 12(1)(20), whose statement you can see here. X comma D is a metric space in which there is a sequence, again just like the previous one, and there are 2 points x and x prime, such that the sequence converges to both x and x prime with respect to the metric D. Then x has to be equal to x prime. This entire thing can be expressed like this. In a metric space, every convergent sequence has a unique limit or converges to a unique point. So let's prove it next. So we want to prove that those 2 points x and x prime to which the sequence converges are actually the same point. So we start by considering epsilon, which is any positive real number. There is an emphasis on this any. Epsilon actually is any arbitrary positive real number. Now because x then converges to both x and x prime, so if we consider this value of epsilon, already we have epsilon, but say this is another epsilon divided by 2, then for these 2 convergences, there will exist integers n1 greater than or equal to m and n2 greater than or equal to m, such that the distance between xn and x is at most epsilon divided by 2 for all n greater than or equal to n1, and the distance between xn and x prime is also less than or equal to epsilon over 2 for all n greater than or equal to n2. That means the fact that xn converges to x is giving you n1, and again because xn is converging also to x prime, that fact is giving you n2, such that these things happen. Okay. Now you consider the maximum of n1 and n2, and let's call that n. That is also an integer, and that obviously is also greater than or equal to m, like the integers n1 and n2, because it will either be n1 or n2. That's what it is. But that simultaneously satisfies this inequality and this inequality. Satisfies means in what sense? That if you put that value of n in place of n here, you see here actually what is going on. What can you say about the relationship between this capital N and n1? Because n is the maximum of n1 and n2, n is greater than or equal to n1. So can you not put n here? Because n is greater than or equal to n1, yes. And that is why for that particular n, this capital N, this inequality will be true. Similarly, n being the maximum of n1 and n2 is also greater than or equal to n2. So here also you can imagine capital N, and that is why this second inequality is also true when, okay, I had to write capital N here. When you take capital N, alright. Now, what are you going to do with these 2 inequalities? Note that they are not exactly the same inequality, because this one involves x, whereas this one involves x prime. Let's see what we can, how we can use these 2 inequalities. So now next we consider the distance between x and x prime, those 2 points. You can use the triangle inequality that our metric D satisfies here with the intermediate point xn. So d of x comma x prime will be less than or equal to d of x comma xn plus d of xn comma x prime. Okay, we are carefully applying the actual triangle inequality here with the proper place of this intermediate point. But then in place of d of x comma xn, you can also write d of xn comma x, because any metric satisfies symmetry. And this one, let's just keep it as it is. And then in the next step, we use these 2 inequalities. Each term here in this sum is less than or equal to epsilon divided by 2. And when you add them up, you get epsilon. So what do you see from this? That the distance between x and x prime is less than or equal to epsilon, And now we recall that epsilon is any positive real number. So what will that any nature of epsilon give us? Any nature of epsilon forces our distance to be equal to 0. But when that happens, the points have to be the same point, and that's how we get the proof. As a small explanation of what can go wrong if we do not conclude this, let us see this part also. Okay, it comes after the proof. I mean, if you already know, you should know, because we have already gone through such arguments many times before, but let us see once more for one last time, say that why we conclude like this, saying that epsilon is arbitrary, so we would have this. Suppose it's not 0, then what goes wrong? Because it's a metric value, it is either 0 or positive. So if it is not 0, then it has to be positive. Now you use this inequality, okay, that this distance value is less than or equal to epsilon for every positive real number epsilon. In particular, you can choose this value of epsilon also, because this is a positive real number, so dividing it by 2 also you get a positive real number. So that means this has to be also in particular less than or equal to this epsilon, that is, this should be less than or equal to its half. But then you can cancel this d value from both sides because it is positive, which will give you the inequality that 1 is less than or equal to 1 divided by 2, which is nonsensical, it's nonsense, absurd. And that is why we must conclude this. So that completes this solution.